Hello everyone, welcome to this video. In this video we'll be looking at the next part for the proof for this theorem which defines spectral family associated with an operator. So we were proving these. In order to prove the spectral family associated with an operator, we have to prove these four things, of which for the first three parts have already been covered in the previous videos. Now we'll be concentrating on this fourth part, where we wanted to prove that whenever we tend this mu towards lambda plus 0, that means we are taking the limit from the right hand side. In that case, the projection operator E mu x, that would tend to E lambda x, right? So here we shall again be using these results which we have already studied, right, relating to the operator T lambda and T mu. So let's move ahead and assume that whenever we assume mu going towards lambda plus 0, we have to prove E mu x tending towards E lambda x, right? So this is our aim here. And also this thing, whenever we prove that this right hand limit would would be there, in that case whenever we tend lambda towards m, in that case the projection operator would become the identity operator. So this is what we will prove here in this video. So here for the proof, let us consider an interval by this symbol delta. Suppose this is some interval delta where we define this to be semi-closed interval with the lower limit as lambda and the upper limit as mu, with mu as closed interval, right? So here with this interval, semi-closed interval, we associate an operator. And what is that operator? Here we use the operator E of delta, right? This operator. And we define this operator to be in terms of the upper and lower limit. How? We associate an operator E with mu. So what is E mu? E mu is the projection operator, right? Which maps whole of the given Hilbert space H onto the null space of T mu positive, right? Similarly, what would be E lambda? It is again an projection operator which maps H, whole of the given Hilbert space, onto the null space of T lambda positive. So these are the two operators, and using these two operators we are defining another operator which is E of delta, and that is defined by the linear combination of these two, where these two operators, they are obtained when we take the lower and upper limit of this interval delta here, right? So this is the construction. So from this construction, because we know whenever we have lambda less than mu, for this the two operators E lambda and E mu, they are partially connected with each other, right, by the partial ordered relation. So it is E lambda less than equal to E mu. This result we already know from part 1. So using this result, because they are related with each other, we have the images of these operators contained in each other. And what are they? They are the null spaces, right? So if you see here, if the two operators, they are related with each other, then the null spaces, they are also related with each other. And moreover, in this case we are not talking about the null spaces, but in particular we are talking about the image spaces. So this image space is related to each other, contained in within each other, whenever these two operators, they are connected with each other. So using this these results here, because we have E lambda related with E mu, E lambda H is contained in E mu of H, right? So this is the result. And moreover, this E delta that we have just defined, that is a projection operator. How this is so? Because by definition, if you see, what is your E delta? It is E mu minus E lambda. So this operator here is a difference of two projection operators. So you already know that difference of two projection operators, that is a projection itself. Therefore this E delta is also a projection operator. Through you can also see this through this theorem. We have already covered this one. Okay, and moreover, this is a positive operator. E delta, that is a positive operator. Why this is so? Because it is a projection, and every projection is a positive operator. Therefore this is also a positive operator, right? So we can use this theorem, right, here, and using this theorem, we can have this result that when you apply E mu onto E delta, let's see what do we obtain. So we can apply the definition of this E delta here. It is E mu minus E lambda. You can open up the brackets, compose these two projections together, right? So that you have E mu square minus E mu E delta, right? Now because E mu is a projection, so it is idempotent, so E mu square is equal to E mu only, and by the result of this theorem, which is marked by equation number 4, you have E mu E lambda is equal to E lambda. Let me show you how. You see P2 P1 that is equal to P1 P2 that is equal to P1. So we can use this result here because we are taking E mu and E lambda as the two projections. So therefore E mu E lambda, they are equivalent to E lambda only. So what is E mu minus E lambda? That is again itself E of delta. So you see we started with E mu composed onto E delta, and that is nothing but E delta itself. So it acts as identity. E mu act as identity on E lambda, E delta, right? So this is one thing. So from here we obtain that E mu E delta is equal to E delta, one result. Another result, let's see what is I minus E lambda applied onto E delta. Let's see what is this. So we can apply the definition of E delta here, right? So this is this thing. Then we can open up the brackets, compose the projections together, so you would obtain these terms. What is E delta square? That is equal to E lambda square, that is equal to E lambda itself. Being a projection, it is idempotent, right? Again E lambda E mu, it is equal to E lambda. Why this is so? This is according to the result that I have just shown you from this relation, right? Okay, so from here we have this as E lambda, then this and this, they cancel out each other, so you have E mu minus E lambda, which is nothing but E of delta. So from all this calculation, you see this term I minus E lambda composed onto E delta, that is E delta itself. So that means this operator I minus E lambda also act as identity onto this E delta. So you have this result. So let's mark both of these results by our equation number 5, right? So I hope this is clear until now. Now for the next part, because we know E delta, this is positive operator, E mu negative, that we already know is positive, and T lambda positive, that they all are positive operators, and moreover these commute with each other. Why this is so? This is in accordance with the result that we have studied about the operators related with the operator T, right? So therefore their products, and moreover they are all self-adjoint. So therefore their products T mu negative E delta and T lambda positive E delta, they are also positive in nature. It is according to the theorem on the product of positive operators, right? So using this result here and using the equation number 5 here, these results, and equation number 2, let's see what is our equation number 2. Equation 2 is these results, right? So using these things, let's see what do we have now. We have T mu E delta is equal to, now in place of E delta, what you can write? You can write E mu E delta, this equation. So in place of E delta, you could write E mu E delta, right? This is one thing. Another thing, in place of T mu E mu, you could write minus T mu negative. How this is so? This is according to equation number 2. What is that? Equation number 2, it is this one here. So using this equation, we have T mu E mu as equal to minus T mu negative. So substituting the value here, we have minus T mu, right? And you know minus T mu negative, that is a negative quantity, and this is a positive quantity. So therefore the product is a negative operator, right? Or you can say not positive operator. So ultimately this T mu E delta, that is less than equal to the 0 operator. And similarly, what is this T lambda E delta, this quantity? Again, in this case we can use the relation from equation 5. This is this one. In place of E delta, we can write I minus E lambda E delta, right? So we can write this thing over here, so that you can shuffle these two terms, so that you have this as not shuffle, we do not require to shuffle it here. Instead we can substitute the value of this term T lambda I minus E lambda. Let's see what is it. It is T lambda positive. From equation number 2, you see T lambda I minus E lambda, it is equal to T lambda positive. So substituting this value here into our relation, we have T lambda positive here, and you know this is a positive operator. E lambda E delta, that is also a positive operator, so the product is also a positive operator. So from here we obtain two relations. One is that T mu E delta, that is a non-positive operator, and T lambda E delta, that is a positive operator. So using these results here, I am writing it again. So these are the results, right? So now you can open up the value of T mu. What is it? It is T minus mu I, right? And again here you can open up the value of T delta, T lambda, it is T minus lambda I, right? So from here you can multiply the operator inside to both the terms, and then shift one of the quantities to the right hand side, so that you have this inequality. Similarly for the second term you have this inequality, and combining both the results we have this inequality with us. So let's mark this as equation number 6, right? Next, if we keep this lambda as fixed, right, because we wanted to take the limit mu going towards the right hand side of this lambda, so we are keeping this lambda as fixed, and we let mu tending towards lambda from the right hand side in a monotone fashion. Monotone fashion means either it is strictly increasing or it is strictly decreasing. So we are assuming the decreasing nature here. So for a decreasing sequence of such kind, whenever we tend this mu towards this lambda, in that case we say that E delta x would tend towards P lambda x. Now why this is so? It is because whenever we have studied about this monotone sequence. So whenever we have a sequence of self-adjoint bounded linear operators, right, which are defined in a monotone fashion, then in that case the sequence is strongly operator convergent, and it would converge to certain limit Tx where this is dependent on x, right? And in this case the limit operator is linear bounded self-adjoint, and it satisfies this condition. So using this result here, we can apply this result onto our sequence of E delta x, right? Because we are tending mu towards lambda, we would have certain sequence. We are doing it in a monotone decreasing fashion. So we are saying this E delta x is tending towards P lambda in a strongly convergent manner, right? So we are defining it like this, and in that case this P lambda would be bounded and self-adjoint. Why? Because it is the limit of that sequence. So the limit here is linear bounded self-adjoint. So in this case it is bounded and self-adjoint. And moreover, you know, this E delta, this is idempotent. Why? Because this is a projection. If that is so, so therefore P lambda is also idempotent. If that is so, because it is P lambda is self-adjoint as well as idempotent, therefore combining these two properties, it should also be a projection operator, right? So therefore P lambda is a projection operator. And using equation 6, so we can see in this equation, if we tend this lambda to we tend this mu towards lambda, in that case your E delta would converge towards P of lambda, right? This is what we are saying here. So using this thing here, we would have from here the value lambda p lambda that is equal to t p lambda. So using this result here, let's see what do we have. So we have lambda p lambda as equal to t p lambda according to equation number 6. Why? Because E delta x is strongly convergent and it is tending towards p lambda of x, right? So we can shift this t p lambda to the left hand side, so that we have, or conversely, we can shift this lambda p lambda to the right hand side, so that we have t p lambda minus lambda p lambda is equal to 0. So we can club the terms, so it is t minus lambda I times of p lambda that is equal to 0. And what is this? This is t lambda. So from here we have the term t lambda p lambda that is equal to 0, right? So we'll be using this result later on. Moreover, from equation 2, we can see what is this t lambda positive p lambda. So we can open up the definition for t lambda positive from equation 2. Let me show you. What is this t lambda positive? T lambda positive is this quantity, t lambda I minus E lambda, right? So using this result here, your t lambda positive is t lambda I minus E lambda. So let's substitute it here in place of t lambda positive, right? So now here we can shuffle these terms, t lambda and I minus E lambda. So it is I minus E lambda, t lambda, p lambda, and the value of t lambda, p lambda is equal to 0. This term is equal to 0. So you have whole of the term as equal to 0 here. So that means ultimately you have t lambda positive, p lambda as equal to 0, right? So you have this term as equal to the 0 operator, right? So we have t lambda positive p lambda x that is equal to the 0 operator for all x which are a part of the given Hilbert space. If that is so, if you look at it more closely, t lambda positive applied onto some quantity is equal to 0. So that means this some quantity is a member of the null space of the operator t lambda positive, right? So we are writing that p lambda x is a member of the null space of t lambda positive, and according to the definition, what does E lambda do? E lambda projects whole of the given Hilbert space onto the null space of t lambda positive. This is the definition of the projection operator E lambda. So basically what is it doing? Because p lambda is a member of the null space, and this E lambda is projecting all the members of this null space onto itself, because it is a projection and it would act as identity on all of the elements of this null space. So therefore it would map p lambda x, E lambda would map all of the p lambda x onto p lambda x only, right? Or in terms of operator, you could, because this thing is true for all x which are the member of the given Hilbert space, so in terms of operator we have this term E lambda p lambda is equal to p lambda, right? So in this case, if we tend this mu towards lambda plus 0 in equation number 5, let's have a look at equation number 5. In equation 5, if we apply this limit here, limit mu tending towards lambda, what results do we have? So in that case, I minus E lambda p lambda is equal to p lambda, because we had I minus E lambda delta E delta that was equal to E delta. Now in our case we are tending mu towards lambda plus 0, right? In that case our E delta is tending towards p lambda. So therefore this whenever we are tending mu towards lambda, so our equation would now become I minus E lambda times of p lambda that is equal to p lambda. This is what we are writing it down here, right? So using these results here, our p lambda is equal to 0. How this is there? Because if you see, if you open up this term, you would have p lambda minus E lambda p lambda, right? This is equal to p lambda. So from here you have p lambda, and the value of e lambda p lambda, that is equal to p lambda from above, from this expression here, right? So therefore you have 0 is equal to p lambda. So you have the value of p lambda is equal to 0 here, right? Remember, because p lambda is 0 and we had our limit e delta x tending towards p lambda x whenever mu was tending towards lambda. So therefore whenever we tend mu towards lambda, in that case e delta x would tend towards p lambda, and what is this p lambda x? That is equal to 0. So therefore your e delta x is now tending towards 0. And what was the definition of e delta x? It was e mu x minus e lambda x, that is tending towards 0. So you could shift one of the term to the right hand side so that your e mu x would now tend towards e lambda x. So that means whenever we have mu tending towards lambda plus 0, we have e mu x tending towards e lambda of x, and this is what we wanted to prove here in this case. So that means the given family E, that is continuous from the right hand side. So this would prove that the given spectrum family, that is actually a spectral family, and it satisfies all the properties of the given spectral family defined on this closed interval small m to capital M. So that means we have proved all the points here in order for this E to be the given spectral family. So I hope you understood this theorem well. Well, that is it for this video. Thank you for watching.